Okay, let's express this function as a power series. Now, we only know how to do this at this point by using a comparison with this as the base series. So this is a power series representation of a geometric series centered at 0, common ratio x, and first term 1. So we know that this converges to, as long as x is within the interval of convergence, to the first term over 1 minus the common ratio. And what we're going to see with all of the example problems that we're going to be working from this section is that even with just this as a reference, we can find power series representations of a lot of different functions, because we can just, rearrange. Here, we're not even going to do any like integration or differentiation. We're just going to do partial fractions and algebraically manipulate, rearrange this to match up with this. But then when you think about, we could also differentiate this power series or integrate it and then match up those forms. It's a lot of versatility. So, okay. So let's first do partial fraction decomposition on this, if it's not already fully decomposed. So can we factor the denominator? Yeah, it looks like so. You've got 3, 1, yeah. So x minus 3, x minus 1. So the form of this decomposition is we've got 2 linear factors to the first power, both to the first power. Okay, now let's multiply by the least common denominator. So 2x minus 4 is equal to a. Okay, when x is equal to 1, we've got 2 times 1 is 2, so minus 4 minus 2, and then 1 minus 3 is minus 2. So b is equal to 1. When x is equal to 3, 2 times 3 is 6, 6 minus 4 is 2, 3 minus 1 is 2, so a is equal to 1. Okay, so what we've got is there we go. So now we can compare these, and these forms we can work with. So what we've got is, so minus 3 plus x, and then minus 1 plus x. Okay, but let's factor out a minus 1 from the denominator. So minus 1 over 3 minus x, and then minus 1 minus x. So there we go. This is, in the right form. But we need to do some work here. So, okay, we're going to factor out a 3 from the denominator, and let's bring the minus 1 out front. So 3, because this is just can be any variable term, right? This is just that. This is any variable term. So remember that. We need to do like a pattern match. The ones need to match up, but this can be like anything. Okay, so and then okay, so minus 1/3 times, and then 1 minus okay, there we go. So if we think about, we know that like a power series representation of a function like this, or just any power series, it doesn't have to be a representation of a function, but a power series is a function, and its domain is the interval of convergence. So you plug in an x, you get an actual value, as long as x is within the domain, the interval of convergence. So what we can see is that this is g of x over 3, positive x over 3. And this is just g of x. It's the exact same thing. Okay? So what we have is f of x is minus 1/3, and then the sum, we just put x over 3 into the power series. And then minus, and then we just actually just rewrite the power series. There we go. So we're not done, but we've gotten through the first kind of big step. This is technically like this is a power series representation of the function, but we just need to clean it up. Okay. So let's try and before we could combine these because the sums are exactly the same, but let's try and do some manipulation on this to let's see if we can just get an x to the n out of this. So, and we'll bring the minus 1/3 into the summation. So we've got minus 1 over 3 times 1 over 3 to the n times x to the n. Okay. All right. So we've got, okay, 3 to the n plus 1, x to the n, okay. Now we can combine these and factor out an x to the n. So this is, let's take out a minus sign. So you've got 1 over 3 to the n plus 1 x to the n. Okay. And I don't think we can do much else with that. So, and, I don't know. I guess I'm kind of tempted to put the minus on the inside just to make it, like a power series as a package. I don't know. So this is equal to, from n is equal to 0 to infinity. Let's do that. So minus 1 minus okay. But we're not done. We want to specify what the interval of convergence is. What's the domain of this function? Now we can't just say, well, okay, here's the common ratio. So when is the absolute value of x less than 1? No, that's only applies for a true geometric series. This is, every power series is very geometric in character because there's this common ratio. But if it's not, if each term outside of the common ratio to the n power, if each term is not constant, then it's not a geometric series. The coefficients are changing for each n, so it's technically not geometric. So we need to do the ratio test. So, okay. Okay, so this makes it, this test, the ratio test isn't quite so simple as it normally is. So let's see if we can combine this. So we've got minus 3 to the n plus 1 over 3 to the n plus 1 minus 3 to the n plus 1 over 1. So that's minus 3 to the n plus 1 minus 1 over 3 to the n plus 1. Yeah, let's use that. It doesn't help. I don't think it helps that much, but so, okay. N plus 1, that's n plus 2. So you've got minus 3 to the n times 3 squared minus 1 over 3 to the n times 3 squared. And then now we flip it and we get 3 to the n times 3 to the first over minus 3 to the n times 3 to the first minus 1. Oh, and then also, wait. And then x to the n times x, and then, okay. Okay. So we've got okay, we can factor out a minus sign from this and from the numerator and denominator. So this is just 3 to the n times 3 squared plus 1 over 3 times 3 to the n times 3 plus 1. Okay, we could maybe factor out a 3 from here. Well, okay, we could take all this out of the absolute value. This is always positive, so we've got 3, and then let's just do, so this is 3 times 3 to the n, so 3 to the n plus 1 plus 1/3 over 3 to the n plus 1 plus 1. So this is 3 to the n plus 1 plus 1/3 over 3 to the n plus 1 plus 1. Okay, now can we take the limit as n goes to infinity of this? That's what we're doing, right? With the ratio test. So this, these are going to the same infinity. And you can think about the adding the, as n goes to infinity, adding this 1/3 in the 1 is negligible. So this is going to 1. This limit is going to 1. So this limit is just going to the absolute value of x. Now this needs to be less than 1 to pass the ratio test. So we know that the radius is going to be 1. But we need to check the endpoints. Okay, f of 1. Let's plug 1 into the series. So when x is equal to 1, 1 to the n is always 1, so is this series convergent? Well, we see that we can separate this into 2 separate series. So this is, okay, well, this is geometric, this is convergent, but this is divergent. So the whole thing is divergent. All right, what about at minus 1? Well, what we're going to get is, this is going to be minus 1 to the n, and then, okay, now we know this is not going to be absolutely convergent because if we just evaluated the absolute value series, but maybe it's conditionally convergent. So let's separate this into 2 separate series. So minus 1 to the n times minus 1, that's minus 1 to the n times minus 1 to the 1, that's minus 1 to the n plus 1. Okay, this is convergent, but this is divergent again. It's like oscillating between like -1 and 0, I guess, or maybe like -2. It's oscillating. It's not converging to anything. So the domain here is -1 to 1, not including the endpoints. Radius is 1, and the interval is just not including the endpoints.